Good morning, everyone. My name is Shreya, and today I'm going to talk about first order RC circuits. In this presentation, I'm going to talk about the different types of RC circuits and their equations of charge, current, and voltage with their corresponding graphs and their applications. Let us now come to the different definitions needed for understanding RC circuits. First, let us know about the meaning of first order circuits. First order circuits are defined by one energy storage element, which in our case is a capacitor in the circuit, and the circuit response to a change in voltage or current is exponential. Now let us learn about the components in RC circuits, which are resistance and a capacitor. The capacitor is a component that stores electrical energy in the form of an electric field. The basic formula for the charge of capacitor is given by charge equal to capacitance into voltage. Capacitors store energy when a voltage is applied across them and release it when discharged. A resistor is a component that resists the flow of electric current, converting electrical energy into heat, and the voltage across the resistor can be given by Ohm's law, which states that voltage is equal to current into resistance. Resistors are used to control the flow of current in a circuit. Now coming to RC circuit, an RC circuit is an electrical circuit that has a capacitor connected in series with a resistor and a power source. A simple RC circuit can be understood by the given figure. The transient period in an RC circuit is the time it takes for the current and voltage to adjust to the conditions after an initial state. The transient response is the change that occurs during this time. The transient period is denoted by t equal to 0 minus to 0 plus. And during the transient period, the capacitor acts as a short circuit. The steady state of a resistor capacitor circuit is when the voltages and currents are constant and there are no changes in the circuit. This happens when the capacitors are fully charged or discharged, and it is denoted by t equal to minus infinity to plus infinity. And when a capacitor is in its steady state, it acts as an open circuit. Time constant of an RC circuit is the time required to charge the capacitor to 63.2% of the value through an applied DC voltage. It is denoted by tau, and the formula for time constant is resistance into capacitance. Now let us come to the different types of RC circuits, which are namely the charging circuits and the discharging circuits. Charging phase occurs when the power supply is switched on and the capacitor stores energy. The current or voltage increases exponentially during this phase, and discharging phase occurs when the power supply is switched off and the stored energy in the capacitor is released. The current or voltage decreases exponentially during this phase. Now let us understand about charging circuits. Let us consider a circuit with a capacitor which is totally discharged and has zero charge in it with zero voltage, connected in series with a resistor and a power supply of EMF E, and at t equal to 0, the switch is closed. On using Kirchhoff's voltage law across this loop, we'll get the equation minus Q by C, where Q by C is the voltage across the capacitor, minus I into R, where IR is the voltage across the resistor, plus E, where E is the EMF of the power supply. On rearranging the terms, we get I equal to C minus Q by RC, and I is also equal to dq by dt. So we get dq by C minus Q equal to dt by RC. And on integrating on both sides, we get the equation of charge across this capacitor, which is Q equal to CE into 1 minus e power minus t by RC, where RC is tau. And differentiating the charge equation with respect to time, we get the equation of current, which is equal to E by R into e power minus t by RC. And we can get the equation for voltage across the capacitor by substituting Q equal to CV in this equation, and we'll get VC equal to Vs, which in our case is E, into 1 minus e power minus t by RC. And we'll get voltage across the resistor by multiplying current in the circuit with the resistance, which is equal to EMF into e power minus t by RC. Coming to the graphs, we can see that the charge versus the time in the capacitor is an increasing graph as Q is constant into 1 minus e power minus x. And as e power minus x is a decreasing function, 1 minus e power minus x is an increasing function. So therefore, the charge versus time graph of the capacitor is going to be an increasing function, which applies the same for the voltage versus time across the capacitor. And the current and voltage across the resistor are decreasing as they are in the format of constant into e power minus x, and e power minus x is a decreasing function. So both of them are going to be decreasing. Now coming to discharging circuits. For this, let us consider a circuit with a capacitor charged initially with Q naught and V naught across the capacitor, which when time equal to 0, the switch is closed and an I discharging current is released across the circuit. On putting EMF equal to 0 in the before equation, we get Ri plus Q by C equal to 0, and replacing I with dq by dt, we get dq by q equal to minus dt by CR. And on integrating on both sides, we get Q equal to Q naught into e power minus t by tau, where Q naught is the initial charge on the capacitor and tau is equal to CR. And I discharging current is equal to minus I naught into e power minus t by tau. And VC can be given by Q equal to CV. So we get VC equal to V naught into e power minus t by tau. And VR is I discharge into resistance, which is equal to minus of e power minus t by RC. And now getting to the graphs, you can see that the charge versus time graph of the capacitor is decreasing. So it is in the format of constant into e power minus x. And e power minus x is a decreasing graph. So we get a decreasing function here. And same goes for the voltage across the capacitor. Whereas the current is minus of constant into e power minus x. And same goes for the voltage across the resistance. So we get that the current and voltage across the resistor are both increasing functions. Now, if we have a question where the capacitor is charging and it already has an initial charge, we can still get the voltage equation for this circuit when the switch is closed. And the voltage is given by V infinity, where V infinity denotes the voltage at steady state, and V naught plus V naught minus V infinity into e power minus t by tau, where V naught is the initial voltage across the capacitor. And let us end the presentation with some applications of RC circuits. RC circuits have many applications in the electrical industry, including timers. So they are used for making devices which require timing, such as pacemakers and intermittent windshield wipers. Low frequency applications such as audio and radio frequencies, musical instruments, voice synthesis, and GPS units. Surge voltage protection. Networks are used to protect against surge voltages by absorbing surges and slowly discharging the pulse. Noise reduction, signal integrity maintenance, and nerve cell transmissions. RC circuits play a role in this transmission of electrical circuits in the nerve cells. Thank you.